right, let's move on to our next speaker, and that's Debra Ceravolo, and she'll talk to us about the colors of Emission Nebulae.
Should I go ahead?
Please.
Okay. Hi, everybody. My name is Debra Ceravolo, and I've been an RESC member for 27 years now. And excuse me, originally from Ottawa, and I've been in BC for almost 10 years. And I've been doing photography pretty much all my life, and astrophotography, I guess, since the Hale-Bopp days. And I got into deep sky imaging about 12 years ago. But I'd like to thank the Toronto Centre for inviting me to come and talk about my favorite subject, and that's colors in astrophotos, and especially nebulae. My presentation it's pre-recorded because the bandwidth here is not dependable, and I haven't subscribed to Starlink. So I guess this would be a good time to go ahead and run that presentation. Hi everyone, welcome to my world on Anarchist Mountain in British Columbia, Canada. We're at about 1100 meters with a sky quality of around Bortle 3, which makes it really great for capturing faint objects like this soap bubble nebula. But it's not always clear, like this time of the year when the temperatures drop, it gets pretty cloudy, like I'm going to show you in a minute. Yes, lots of clouds above, clouds below, and a lot of the time we live in the clouds. So obviously not a lot of imaging going on then. But having a permanent observatory means that I have the luxury of being ready when it does clear. I'm having some fun with some time-lapse photography here. Here is a view of my observatory in much nicer weather in the summertime with the Milky Way. You might think that the scope looks kind of small in such a big 12-foot dome, and you would be right. There is a much bigger instrument destined to go in there. But this is a 12-inch astrograph, and I will show you the details of that in a moment. So this is what is intended to go in the observatory. It's been designed by my husband, Peter Ceravolo, and is actually going to fit in that 12-foot dome. It's a very fast system, about an f4.5. It's a 900 millimeter aperture, about 36 inches. He says it's 90% finished and 90% to go. He still has to finish the mirrors, but the mount shown here is running well and will be installed this coming spring. Just the mount. We will attach the existing scope on it until the mirrors are finished, but what a killer mount. No wind will move that around. I have been doing astrophotography for probably a dozen years now, and my approach and techniques in processing are always evolving. I tend to stay on an object for long periods of time, pretty much as long as it's visible overhead. I typically acquire 25 to 35 hours of data on any object now. This is a telescope I've been using for the past couple of years. The scope is a Ceravolo 300 millimeter astrograph designed by Peter, and it's a dual configuration, meaning I can swap out two sets of corrector lenses and go from an f9 or 2700 millimeter focal length to an f4.9 1400 focal length, sort of like a focal reducer for wider field, depending on the camera it's coupled to it. Here it's at f9 with an SBIG STX 16803 camera, and it has an off-axis guider and filter wheel set with Astrodon filters, sitting on a Paramount ME2 mount. With this setup, I can get about a 0.6 arc second per pixel resolution. And on the top is an Eagle 4 Pro computer that allows me to plug in all the cables for the cameras and the focuser and the mount and everything, eliminating the bulky power bricks and keeping everything neat and together. It's especially nice when the scope's loose, wires don't get pulled out or strangled. In this photo, I am swapping out the big 16803 camera for an Illuma 694 mono camera with its filter wheel, staying with the f9 configuration, giving me a resolution of 0.3 arc seconds per pixel, but a much smaller field of view. This is really a great setup for planetary nebulae. This camera doesn't have an off-axis guider, so I have attached my pointer here, another guiding camera with the mirror lens, and I can easily find a guide star better with this wide field. The problem with off-axis guider chips is that they're usually small fields and you may not be able to find a good bright star to guide on. I'll just quickly show how I do the acquisition and then move on to talking about color and nebulae. This is the Eagle Manager from the computer that was on top of the telescope you saw earlier. I log into it from inside the nice warm house remotely, and I can turn on the cameras, and I make sure that everything is operational with all the USB ports. I look at the temperature and the sky quality meter. It's a really handy, nice little thing to have. So while I'm accessing the remote desktop, I can activate the SkyX software. That's the planetary software that comes with the Paramount. I can do many things with this software, but I mostly just use it to find my target and to slew the telescope. There's also a virtual hand paddle there where I can center the target if the pointing is not perfect. And I can also keep track of where the telescope was pointing all night and if it's getting too close to the horizon. For my main acquisition software, I like to use MaximDL. It connects the cameras, sets the coolers. It's also a scheduler where I can choose what filters will be used, how long the exposures will be, how many images to take, and where to download the images. MaximDL also controls the guide camera. For processing my images, I mostly use PixInsight where I can do all the calibration and post-processing, and sometimes I use Photoshop at the end. I prefer CCD monochrome cameras with separate filters because it gives me better control over color, and they are usually less noisy than one-shot color cameras or CMOS cameras. There are some CMOS mono cameras that are really good too, but I use what I have, and that's a couple of S-Big mono CCD cameras. Here I am taking apart a 7-slot filter wheel for cleaning that goes on an S-Big STX 16803 full format camera like the one you saw earlier on the telescope. These are large 50mm Astrodon filters. There's luminance, red, green, and blue, and 3 narrowband filters. Narrowband filters are a must for capturing the detail in nebulae as they isolate the emissions coming from the objects. So in order to talk about colors of nebulae, let's start with what nebulae are and how colors are created within them. I'm sure most of you probably are quite aware of what a nebula is, but I'll just talk briefly as I move into dealing with color palettes and my own technique that I've developed. We can colorize our images any way we want, and that's fine, but I usually like to better represent the object I am photographing more accurately. And in order to do that, I needed to tune into the physics to gain a better understanding of what's happening inside the nebulae. So here's a little science lesson. Throughout our galaxy, floating in space between the stars, exist gigantic cosmic clouds of dust and gas. The extreme cold temperature causes the atoms in the gases to bind together and form molecules that coalesce into denser regions. Some of these dense regions of gas collapse under its own gravity, and star formation begins. Very hot newborn stars energize the surrounding gas with ultraviolet light, making the clouds visible at optical wavelengths and giving us amazing things to see and photograph. There are basically 3 types of nebulae that are technically different from each other. There's the dark nebulae, reflection nebulae, and emission nebulae. Planetary nebulae and supernova remnants are also emission nebulae. Dark nebulae, like this Horsehead Nebula, are these irregular and familiar shapes made of dust clouds so dense that they obscure the visible light from behind, making them appear opaque. They are being backlit by bright ionized gases. The Pleiades on the right, M45, is a good example of a reflection nebula. This type of nebula typically shines with a beautiful blue color as the dust grains in the cloud reflect the blue starlight back to us. And this close-up of the Orion Nebula at the bottom is an emission nebula. This nebula itself is creating its own light. Note that planetary nebulae are still emission nebulae, but they have a different origin. Planetary nebulae are the expelled atmosphere of a single dying star that is in the process of collapsing. You can usually see the star in the center, like in the Helix Nebula here, and the center star in the Owl Nebula. The extreme hot core of the star has been exposed, and its intense heat is ionizing the surrounding shell. These are the hottest known stars in the universe and create fascinating and beautiful, colorful, and short-lived objects, usually roundish, like a planet shape, hence its name. Most interestingly, this process will be the fate of our own sun. Many factors influence the color of emission nebulae, including the nature of the chemicals that make up the cloud and the degree to which these gases are being ionized. But I have also learned from experimenting with certain filters that the expanse of interstellar dust in and around the nebula and along our line of sight can alter the emitted color, and I will show what I mean about that later. Back to the Orion Nebula. This is a close-up of the core, and these hot young stars in the center here in the center is called the trapezium cluster, and they are radiating powerful ultraviolet light, causing the atoms of the surrounding gases to absorb all that energy. In simple terms, when the excited atoms settle down, they release that extra energy it absorbed as a photon that emits at a specific wavelength, and then we correlate that wavelength to a specific color in the visible spectrum. So different gases emit at different wavelengths. Again, I realize most of you know this stuff, but just a little review here. By definition, the visible spectrum is the part of the electromagnetic radiation that human eyes can detect. This ranges from wavelengths of approximately 400 to approximately 700 nanometers. Hydrogen is by far the most abundant element in the universe, and naturally the dominant gas in emission nebulae. Other elements that also exist in the interstellar medium are helium, oxygen, sulfur, nitrogen, and there are others. So here are three of the most prominent elements in most nebulae: oxygen, hydrogen alpha, and sulfur, which became the most popular filters available for astronomical cameras. By the way, here's an interesting point. Color is a biological concept. Photoreceptor cells in the human eye, called rods and cones, respond to light waves, which our brain converts to our perception of light and color. We have three kinds of cones that are sensitive to different wavelengths. One kind is sensitive to short wavelengths, like the blue range. Another is sensitive to medium wavelengths, like the green range. And one is sensitive to long wavelengths, the red range. Color is not a feature of light, but only an impression produced by an electromagnetic wave of a certain length in the brain. In other words, color exists because our brain creates it. People's ability to see color vary, but for the most part, we all see similar colors, unless there is a deficiency, which can occur. I want to make a key point here. Any color is a mix of red, green, and blue in different proportions, giving us roughly 16 million colors that can be reproduced in an RGB image. So determining those three RGB contributions of a color, we can pinpoint and reproduce an accurate color of any wavelength. There is a way that we can do that in Photoshop, and I will show that in a moment. Cameras have filters that allow certain wavelengths through, and we can play with that in a multitude of ways. We can be playful with it or more scientifically accurate, whatever the astrophotographer wants to do. Right here, I would like to say there is no right or wrong way to produce an astronomical image, unless there's been an introduction of something that was never there, but that's a whole other thing. How someone colorizes their image is totally up to them. It's a personal thing. My thing tends towards the more accurate representation, but it is fun to explore and experiment. So here I will talk a little about color palettes. When talking about color palettes, you have to talk about the Hubble palette first, so a little history here. The Hubble Space Telescope captured this famous image of the Pillars of Creation in the Eagle Nebula way back in 1995. And the way they colorized it was for a reason. The scientific camera was not equipped with normal red, green, and blue filters, but instead hydrogen alpha, oxygen, and sulfur filters to better capture the structure and detail of the object by isolating the emissions. Now, in photography, there are three primary colors, red, green, and blue, that make up a naturally colored image. So to create a naturally looking photo with three narrowband filters, the Hubble imaging team had to force the narrowband data into the broad RGB channels. This is how the colors of Pillars of Creation came to be. Notice that H-alpha, sulfur emissions are both close together in the red end of the spectrum. The pillars was colorized by assigning S2 to the red channel, and instead of also assigning H-alpha to the red, as that would not differentiate the structure, it was colorized green. So they put H-alpha in the green. The O3 emission, the oxygen line, was assigned to the blue channel. But since hydrogen alpha was colorized green and is the most abundant gas, the Pillars of Creation was known to be predominantly green, and this combination became known as the Hubble palette. However, the Hubble palette is not the only way to combine color. Those three filters can be creatively rearranged in the RGB color channels to produce different palettes, with a wide variety of colorful and dynamic presentations. The palette names are acronyms, with each letter representing the emissions arranged in the order of the red, green, and blue designations. The Hubble palette, now known as SHO, is where sulfur, S2, is assigned the red channel, hydrogen alpha to the green channel, and oxygen to the blue channel. Another less often used palette, often seen in CFHT observatory images, is the HOS, where they put H-alpha in the red, oxygen in the green, and sulfur in the blue. Alternately, HSO has a pleasing result with more pinks and purple colors. The HOO palette portrays a more natural coloring with hydrogen alpha as red and oxygen as both green and blue, as O3 naturally resides between green and blue along the spectrum. The outcomes of these combinations vary depending on the object being imaged and the intensity of the different emissions from that object. Also, one can tweak each color channel to different degrees using contrast manipulation or curves and modifying the palettes. All of these palettes and modified palettes offer interesting ways to explore emission nebulae. Depending on the object and the palettes chosen, different structures in the nebulosity can be highlighted. Creating images from narrowband data using a variety of those palettes can make the star colors in an image look pretty ugly. This is M27 with the HOS palette. It is important to note that stars emit light over the entire continuous spectrum, and the narrowband filters don't allow that whole spectrum through. So they look smaller with weird colors, usually magenta. One solution to achieve properly colored stars in narrowband images is to acquire two sets of data, one taken with RGB filters for the stars and one set taken with narrowband filters for the nebulae. To summarize, you remove the unwanted stars from the narrowband image of nebulae and later replace them with the naturally colored RGB stars. There are image processing tools like my favorite Star Exterminator, a plugin for PixInsight, that can effectively remove the stars from the narrowband image while leaving the nebulosity intact. Also, further processing on the starless image allows the freedom to stretch out more detail without worrying about bloating the stars as they are later blended back in. Here I have removed the stars in PixInsight using Russell Croman's Star Exterminator, an amazing plugin that works really well, which looks kind of cool and would make an interesting photo on its own. By removing stars, we can often see much more detail in the nebula. The Star Exterminator plugin also creates an image of just the stars that it removed, which can be processed on its own as well, like using deconvolution, reduction, and then put back into the starless image. The result is an image with good structural detail in the nebulosity and properly colored stars. I won't demonstrate how to do all that because there are some really good videos on YouTube. I really think that good star color is important. So I take two sets of data when I'm imaging, RGB when it's dark with no moon, and narrowband data when the moon is out. Narrowband filters only let a sliver of light through, so that makes them great for moonlit nights and also in places where there is a lot of light pollution. So here is the before image, and here's after with the properly colored RGB stars. So, can we have natural color using only narrowband filtered images? I think so. My approach is not scientifically accurate by any means. Keep in mind there is really no such thing as perfect or true color, but we can get close. First, here I want to show a typical way to create a color image from monochrome images. This is a screenshot in PixInsight and how we put together master images to get a color image. Here I have three narrowband images. There's oxygen, hydrogen alpha, and sulfur. Or I could just have red, green, and blue, whatever. So you basically enter the names here in the channel combination into the red, green, and blue channels here. And you hit the apply button and a new image comes up in color. You can see there is sulfur in the red channel, hydrogen alpha in the green, and oxygen in the blue. That's the Hubble palette. I can switch them up and get different color palettes if I want. But here's the thing. By assigning the narrowband images to those three channels, we are telling it to be pure red, pure green, and pure blue. Remember, every color has a red, green, and blue component, and pure red, for example, has no green or blue component. Same with the other channels. So that's okay if you want your image to be one of those palettes I talked about. But if you want the color to be more accurate according to the narrowband's specific wavelength, you have to determine the contributions of red, green, and blue for each wavelength. I have found the best way to determine the red, green, and blue values for each wavelength is to use the color picker tool in Photoshop. There I open a calibrated spectrum with the wavelengths in nanometers created by Andrew T. Young of San Diego University here. I can get a close approximation of the combination of red, green, and blue components of each wavelength by touching on the number of the wavelength in nanometers on the spectrum for each emission with the eyedropper, and here is showing it's touching around 656 nanometers, which is the wavelength of hydrogen alpha. Then we are given the information we need in the color picker tool. So here we have the contribution of the red, green, and blue values that make hydrogen alpha, and you can see that there's no green contribution, but there is a blue contribution. In the past, I have stayed in Photoshop and used hue saturation layers to enter the values and colorize the image because I didn't know how to do that in PixInsight. But now I have been collaborating with a friend, Tim Hutchison, who figured out a way to do the same thing using a process in PixInsight called pixel math. That allows me to state the red, green, and blue contributions of each wavelength and then tell it to combine the images that way. I won't bore you with the nerdy details of the math, but Tim converted the information of each emission to the PixInsight standard of measuring color and the coding which makes the pixel math work. So that is the basic idea of colorizing nebulae, and I will show you some finished examples in a moment. But right now, I want to take it a little further with some imaging work that I've been doing for the past couple of years, and that is working with a rarely used filter, hydrogen beta. This is probably better suited for a whole other talk, but my work with hydrogen beta has been interesting and I think can show us a different way of appreciating the dynamics of nebulae. Some may think, what's the point? It's still hydrogen. The structure should be the same, which it mostly is, but there is something else interesting about it. It emits in the blue end of the spectrum. Hydrogen possesses many other emission lines that exist throughout the entire electromagnetic spectrum, even beyond the visible. You can see 4 of them here in the visible. But the second brightest hydrogen line after hydrogen alpha is hydrogen beta. Here at 486 nanometers, the blue end of the spectrum, making it an interesting contribution to an image. If hydrogen exists anywhere in space, hydrogen beta is there too, along with all the other lines, albeit fainter than hydrogen alpha. However, galactic dust will be the defining factor of how much we can see it. Dust can attenuate hydrogen beta, much like the reddening of the sky at sunset, where blue light gets scattered by the atmospheric molecules near the horizon. And so likewise, galactic dust can scatter the fainter blue hydrogen beta light, leaving the red hydrogen alpha to dominate, like here on the left. The Gecko Nebula is very red naturally. I'm assuming there is a lot of galactic dust there. Not so much H beta is getting through. It's there, but it's getting scattered. Remember, wherever there is hydrogen alpha, there are all the other hydrogen lines too. But where there is less galactic dust in the region to scatter the blue emissions, hydrogen beta shines through, causing the nebula to appear more magenta, as you can see here in the Orion Nebula. The resulting colors I get with the combination of using hydrogen alpha, hydrogen beta, and oxygen filters and mapping them according to their spectral wavelengths is different. This is a basic diagram of mixing light and is known as the additive color theory. When all the primary colors are added together, the light is white. When there is no color or absence of color, there is black. Our sun is white light that holds all of the colors we see. This only shows the primary and secondary colors, but of course, there are many more combinations. And it's very simple, but depending on the intensities of the intermingling of different wavelengths, you get a variety of color, and the more colors involved, the lighter the result. On the right-hand side, you can see the bubble nebula, and on the edge of the bubble nebula is kind of a gold color, which is a combination of the oxygen and the hydrogens. And you can see the pink nebulosity all around it, which is showing the H beta shining through in the background there. So without galactic reddening of the hydrogen gases, you will see the magenta. Here's an interesting fact. Back in the film days, objects like the California Nebula and Horsehead Nebula looked really red because film was not that sensitive in the blue end. It wasn't showing the hydrogen beta contribution. The film in those days was actually optimized and intended for portrait photography, so more towards the red. So the green-blue oxygen also interacts with all the other emissions, creating varying shades of pale greens and yellows, like in the bubble. By understanding how light color theory works, we can begin to appreciate the dynamics of the dust and gases in space. Finally, here are a few images that I have processed using hydrogen alpha, hydrogen beta, and the oxygen filter, and color mapping them using the pixel math method. The photos have had the narrowband stars removed and the RGB stars inserted at the end. You have already seen the Bubble Nebula and the Trapezium in the Orion Nebula. This is the Elephant Trunk Nebula in the constellation Cepheus. I think it looks more like a dragon's head. The intense emissions around the snout here, see the dragon head here? There's like his nostril there. The intense emissions around his snout here are very magenta, so you would think less dust there. It makes me wonder if the intensity of the ultraviolet radiation from the new stars is pushing away that galactic dust. This is NGC 7000, or the Cygnus Wall. That's part of the North American Nebula. And there's lots, you can see there's lots of hydrogen beta, very strong in this image. The Running Man Nebula, which is just above the famous Orion Nebula. Actually, Orion Nebula is off in this direction over here. And it's very pink and lots of H beta shining through there. And of course, it was spectrally mapped like I showed earlier. And of course, the famous Horsehead Nebula. It's kind of red, but also a little magenta. So a lot of galactic dust there, but the hydrogen beta is still contributing to the overall color. This is a crescent nebula, and it's pretty wild. The teal O3 is strong, and those light yellows is a combination of hydrogen and oxygen. The red H alpha in the crescent and hydrogen beta in the background. This looks like a supernova remnant, but it isn't. It's an emission nebula. It was formed by the fast stellar winds of a massive, really energetic dying Wolf-Rayet star colliding with and energizing the slower moving winds it ejected at an earlier time. That resulted in a shell and two shock waves, one moving outward and one moving inward. So much structure there. Lastly, this is the soap bubble nebula. Notice the light yellow in the outer rim of the shell where oxygen and hydrogen are overlapping. The background has lots of rich magenta due to the less dust there. This is a very faint object, and I got 45 hours of data on it. By the way, this kind of imaging is very intensive and requires Zen-like patience and really good guiding, and basically I threw out about 25 hours of data. So doing this kind of imaging is really hard and takes a lot of patience, which I don't always have a lot of. But we astro imagers are all really crazy anyway. My cat will attest to that. He is telling me, enough of this image processing and feed me. How we choose to display our celestial photography is an individual choice, but there should also be a consideration of the object that we are capturing and disclosure about how we are representing it. Color is an important and powerful tool, and the colors of the universe can teach us a lot. Thank you for listening. I can't hear you, Paul.
I have to repeat what I just said? Okay. All right. So I'm told that I have to repeat what I said. I said, Deborah, fabulous presentation and, of course, great images. And thank you very much. And I'm glad that I found you on the internet and invited you over to speak to us. Let's go to questions.
Great. We got a few questions in here. First question, at what elevation is your observatory?
Oh, the elevation is about 1,100 meters, which is about 3,600 feet. We're actually about 2,000 feet above the valley floor in the Soyuz.
Great. Okay, next question. Considering that HO has a more natural feel as opposed to, say, HOS, at least to my eyes, do you consider this an indication of S2 basically providing additional information with regards to the hydrogen alpha filter?
Sorry, I don't get the question.
Okay.
Just repeat that. I can't read it.
Yes. So considering that HO has a more natural feel as opposed to, say, HOS, at least to my eyes, do you consider this an indication of S2 barely providing additional information with regards to hydrogen alpha filter?
It's just more natural because oxygen resides both in the blue and the green and is really a teal color than anything else. So the HOO palette is basically correct in the mapping. But the sulfur is an interesting filter on its own. It actually allows through a very different structure than H alpha. So that's why the Hubble palette comes through so well, because it really shows the difference between the sulfur and the oxygen. So the sulfur, yes, sure, they're both kind of close red in the spectrum, but they both offer different structures of the subject itself. Does that make sense?
Yep. Okay. Next, we have a comment from Peter West who says, "Thank you for including a basic explanation and not assuming some of us actually know anything. Simply amazing presentation."
Great, thanks. I wasn't sure, where to go from the novice to the more advanced, but I just kind of like put it somewhere in the middle there.
Next, we have a comment from Guy who says, should we just skip S2 for using hydrogen alpha for nebulas? What should be green if it was not oxygen 3?
Well, it all depends on what palette you want to use. I wouldn't skip the S2. I actually, because I use the H beta all the time now, I took my S2 filter out because I only have 7 slots in my filter wheel. I use luminance, red, green, and blue, hydrogen alpha, hydrogen beta, and oxygen. But sulfur is actually, sometimes I wish I had it because some objects show a very strong structure detail in sulfur, depending on the object. Like for example, the Helix Nebula has very strong sulfur structure that whatever channel you put it in, even if you combine it with H alpha, it will show through and add to the image.
Great, thank you. Next up, we have, sorry, Guy also says, why did I purchase that S2 filter for crying out loud? To which we did actually get a response in the comments from Eric Briggs, who said that CCD imagers are very sensitive in the red, so S2 is trying to be your friend. What do you think?
Yeah, I mean S2 is a good filter. I would like to get back. Maybe I'll get a new filter wheel that has 8 slots, and I'll put my filter, the S2 filter in there. But it's not a waste of money, that's for sure. But it can be color mapped like I did, and just included into the image the way I do my my mapping, just the same way.
Follow up to that, we actually says, just wondering how much extra information I can get from S2 when I already have captured an hydrogen alpha imaging run.
Well, like I said before, S2 can offer a very different structure.
Right, of
than
course.
the H alpha.
Next question comes in from Lewis, who asks, how many different cameras do you use? Do you have to update them often?
Updating? No, I have mostly S-Big cameras that I've had for a long time. One's the 16803, the really large format, and the other is it's a 694, which is a 4 micron camera that I love to use for with my F9 setup, which is like really high resolution for galaxies and planetary nebulae. So I basically just mostly bounce between the two of those cameras, but not often because it's a lot of work to change out.
That makes sense, yeah. We got a question in from Warren Gallagher, who wants to know, does the star eliminator have a problem with larger star-like objects?
You mean the Star Exterminator?
Yeah, I think so.
The software. I find that what was it called? StarNet Plus in the past in PixInsight was terrible, and it really had a hard time with large stars. But the Star Exterminator, I'm actually really impressed with. It does an excellent job on the small stars and the large stars in particular. So it's very much worth the small cost, I think. It's actually Russell Croman's processes that he's created. Another one called Blur Exterminator are real game changers in the image processing world right now.
That's very cool. Question coming in from Aiden B, who wants to know, how much of the hydrogen delta and gamma wavelengths are you able to get in your photos?
Well, I don't get the delta and gamma at all because I don't have the filters, for one thing. And they are very faint. But it's not to say that I won't do that one day. I will. I think normally when I do an image, I go very deep, probably somewhere between 25 and 35 hours for every object. And I tried to get as much or equal data with everything. Like if I get, say, 20 hours of H alpha, I'll try to go for 20 hours of hydrogen beta as well, and then the gamma and delta. But it's not an easy thing to find those filters right now, unless somebody comes up with making them mass produced.
That's great. I think that's the last question for tonight. Thank you so much.
Great. You're very welcome.